All right, let's talk about electron configuration. So, electron configuration is a way of writing out what electrons are present in an atom. So, electrons will fill orbitals one at a time from the lowest energy to the highest energy. We'll talk about the exact rules that regulate that. And the way you write out the electron configuration, you write it as the n value, the orbital letter, superscript the number of electrons in all those orbitals. Okay? Now, the periodic table is laid out in such a manner as to give you what is the highest, orbital. So this is the s block. This is the p block. This is the d block, and this down here is the f block. So if I'm anywhere in these two columns, then my highest value is going to be S. If I'm anywhere here, it's going to be P, D, and F, right? And then the period tells you the N value. So if I'm on row 1, N is equal to 1. Row 2, N is equal to 2. 3, 4, 5, 6, 7. Now you might have noticed that the D's and the F's are a little bit different. We're going to get to that. So hydrogen, for example, my first one is going to have is 1s and has 1 electron. So we'd write it as 1s1. Helium is also 1s and it has 2 electrons. So we write it as 1s2. Beryllium, sorry, that should say lithium. Right, lithium right here is 1s2, so it's got both of those electrons, plus 2s1, the first 2s1 electron. And so every single element will have all the electrons that came before it. So the electron shells, as I just said, are indicated by the periodic table. The d orbitals will always have a value of n minus 1. So here's the n equals 4, 4s, and 4p, but in the middle is 3d. And then the f values, so you go 4s2, 3d, and this is 10. F orbitals have an n minus 2 value, so you go 6s, right, 6s, then 4f, 14. Okay? Now there is a rhyme and reason for why that's the case. We're going to get to that. So then how do you write an electron configuration? There's a couple different ways. So the standard notation is you write lines designating the number of subshells, which of course is 2l plus 1. And then for any given n plus l value, 1s, 2p, 4d, those subshells, those individual orbitals are going to be this degenerate, meaning the same energy level. You put an up arrow for spin up, and you put a down arrow for spin down. So here we go. The 1s orbital, right, has one possible L value, or ML value, 0, right? There's only one s orbital. The 2s, only one orbital. 2p has 3 possible orbitals, right, 2l plus 1. Then 3s, 3p, 4s, 3d, right? D has 5 orbitals. Now, why are they in this order? Again, we're going to get to that, but there is a way to figure out what order they go in. But this is how you would write out orbital notation. And so, generally speaking, you'll see arrows like this on if it's done in a computer program. But if you're writing it, typically the convention is to write a half arrow for 1 electron, so spin up, spin down. And then you have box notation, where each orbital is written as a box, and then it's just like a little bit cleaner. So my 1s orbital is written as a box 1s, then 2s, and then 2p is 3 boxes conjoined because it's 3 orbitals, right? And you can see here that this is a more handwritten example where it's half arrow up, up, up. And why is it up, up, up? Well, we'll get to that. And then finally, we have SPDF notation. This is the most common way. It's a very truncated way. The only thing it doesn't tell you, there's some information that it doesn't tell you, but it's the easiest way to do it. Okay, so you write the energy level of the electron, and then to the sublevel to the number of electrons, right? So 1s2, 2s2, 2p5, and you don't move on to the next subshell until you finish the previous one. So let's talk about the rules that we follow when we do this, and you'll see why. How to figure out the energy levels, why were those all unpaired spin up, and and other things like that. So there are 3 major rules that we follow when we're writing out electron configurations. The first one is called the Pauli exclusion principle. And the Pauli exclusion principle states that you cannot have 2 electrons with the exact same set of quantum numbers. Remember, quantum numbers are our address, N, L, ML, MS, right? You cannot have 2 electrons with the exact same set. So because you only have 2 possible values for MS, that means that any combination of NL and ML can only have 2 electrons. So for instance, if I have N equal to 1, L equal to 0, ML equal to 0, which represents our 1s orbital, then I can have plus 1/2, and I can also have 1, 0, 0, minus 1/2. Okay. Well, I cannot put any more electrons here because I cannot have any more electrons in the 1, 0, 0, let's say neighborhood, right? Let's say that's the neighborhood and this is the exact house, right? I can't have anyone in that neighborhood because I've run out of spaces. So the next thing I'm going to go to 2s, 2, 0, 0, plus 1/2, 2, 0, 0, minus 1/2. Okay, now that one's full. Now we go to 2p, 2, 1, negative 1, minus 1/2, 2, 1, negative 1, plus 1/2. Okay, so there are 2 electrons in 1p orbital, okay, the negative 1. And then 2, 1, 0, plus or minus 1/2. And 2, 1, plus 1, plus or minus 1/2. Okay, so s orbitals can have 2 electrons. P orbitals can get 6 electrons. D orbitals can get 10 electrons. And F orbitals can get 14 electrons. Because you get 2 electrons per orbital, per subshell. S has 1, P has 3, D has 5, F has 7. So you double that to get the number of electrons that can get in there. Cool. So each orbital can only hold 2 electrons, one spin up, one spin down, right? So I can't have 2 spin up in the same orbital, right? I can't have 2 spin down in the same orbital, and I couldn't do up, down, down. I couldn't have 3 electrons in 1s. Okay, that's the Pauli exclusion principle. It basically means you get 2 electrons per subshell, then you move on to the next one. Hund's rule, which doesn't matter for s orbitals, but does matter for p and d orbitals and f orbitals. When filling degenerate orbitals, remember degenerate means same energy, you fill all the orbitals with spin up electrons before adding any spin downs. Spin ups first, then spin downs. The reason for this is, remember we said that spin up is lower in energy. Okay? And nature always tries to go to the lowest possible energy state. So all spin ups, because this is technically lower in energy. Up, 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 and then you would start pairing down, down, down. So you fill the orbitals half filled first, then you pair. Because spin up electrons are lower in energy than spin down electrons. And because of this, half filled orbitals are lower in energy than partially filled orbitals. So this configuration is lower energy. This configuration is higher energy. And then finally, we have the Aufbau principle. This one's very straightforward. You fill the lowest energy orbitals first. That's it. You fill up the lower energy orbitals, and then when you run out of room, you move to the next highest. Now, how you determine relative energy levels, you use the N plus L rule. So, the lower N plus L value has lower energy. So, if we look at 1s versus 2s, well, this is 1 plus 0. This is 2 plus 0. 1 is less than 2, so 1s is lower energy. Okay? In case of a tie, the lower n value is lower in energy. So the 2s orbital, or the 3s orbital versus the 2p orbital, okay? 3 plus 0, 2 plus 1, 3 is equal to 3. However, this has a lower n value because 2 is less than 3. Therefore, 2p is lower in energy. That's how it's determined. Okay, and that's why you end up going 4s, 3d, 4p, because you have 4 plus 0 or 4. Man, 4 plus 0 or 4. You have 3 plus 2 or 5. Then you have 4p, which is 4 plus 1 or 5. And then you have 5s, which is 5 plus 0 or 5. Okay, so this is obviously the lowest. And then you have 3 5s. And you break in order of the n. So 3, so this one's second, then 4, so this one's third, then 5. So this one's fourth. And from that method, you can see where does the first F show up. It shows up after 6S, right? Because you have 6S, 4F, 5D, 6P, 7S, right? 6 plus 0 is 6. 4 plus 3 is 7. 5 plus 2 is 7. 6 plus 1 is 7. 7 plus 0 is 7. So these all have a n plus L value of 7, and so you order them from lowest n to highest n, 4, 5, 6, 7. So you can see on this chart that as you go down the n values and across the L values, so L equals 0, all your s orbitals, p orbitals, d orbitals, f orbitals, you go on a diagonal from L down to n. So 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, 7p, 8s, right? And go along the diagonal. And realistically, you don't need to go past this because our periodic table doesn't go that high. So even though technically you can have like functionally any value for n and L and ML or whatever, right? You're never going to go above 8 because that's the number on the periodic table. There's no more elements. I mean, there could theoretically be more, but they're functionally useless because they're so unstable. They break apart the instant they come together. So, with that said, let's shift gears a little bit and talk about two properties of atoms that we can see from, or we can determine from the electron configuration. So the first is diamagnetism and paramagnetism. So basically, if you have unpaired electrons, you can align to a magnetic field. Okay, so if you have at least one unpaired electron, and 1 to however many possible, the maximum number possible would be 7. But if you have at least one unpaired electron, you are considered paramagnetic, and you are attracted to a magnetic field. If you have 0 unpaired electrons, then you are diamagnetic, and you are not attracted to a magnetic field. Okay. Now you can see this. So for example, if you look at the box notation for nitrogen, okay? So I've got my 1s box, my 2s box, my 2p boxes. It's nitrogen is 1s1, 2s2, 2p, 1, 2, 3. So as you can see, I've got 3 unpaired electrons. But if I look at something like helium, helium is 1s, 1, 2. So helium would be diamagnetic, and nitrogen would be paramagnetic. This is why most, not all, but most metals are magnetic, because they have unpaired electrons. There's also ferromagnetism, which is a little bit different. You don't really need to worry about that. It's paramagnetic, but even more so, right? So metals, because of the way they're kind of loose and free with their electrons, have a much stronger attraction to a magnetic field than a non-metal would. But the thing is, SPDF notation, right? If I just say 1s2, 2s2, 2p3, that gives you no information about the electron spins. So SPDF notation does not tell you magnetism, or para or diamagnetic. The other thing we can deduce from the electron configuration is called the effective nuclear charge. So electrons are attracted to protons in the nucleus, positive and negative charges, but the outer electrons can get blocked by the inner electrons. So when an electron passes in front of another electron, negative charges are repelling. So the further out the electron is, the more diminished the pull towards the nucleus. Okay, so we call this effective nuclear charge. It's Z star or ZF, and it's simply equal to, it's very simple. It's for Z star for any electron you're looking at, and you're looking at shells. Okay, so you're looking at like 2p, 3s, 4f, those sorts of things. Is going to be equal to the atomic number of the element, because that's the number of protons, minus the number of electrons between you and the nucleus. So if you're in the same orbital, you don't screen each other. So if you look, let's look back at nitrogen. Okay, so nitrogen, 1s, 2s, 2p, 1, 2, 3. Oops, I should have these first. Okay, this electron is being blocked by these 4 electrons. These 2 electrons are not blocked by this electron. They're only blocked by these other 4 electrons. So these 3 electrons all would have the same effective nuclear charge. And so for these guys, your effective nuclear charge would be the number of nitrogen, which is 7, minus the number of electrons between you and the nucleus. So for 2p, it's the 2s and the 1s, or 3. And then as you travel across a period, for any given electron, you're going to increase the effective Z, right? So let's look at sodium, aluminum, chlorine. These are all in the same period, same row. So the electron configuration for sodium is 1s2, 2s2, 2p6, 3s1. Aluminum is the same, 3s2, 3p1. And then chlorine goes all the way up to 3p5. Okay, and we want to know for the 3s electrons, so only these electrons here. So these electrons don't actually matter because they're not screening us. They're behind us, so they're not getting in our way. Okay, so here are the electrons that are screening me, and here are the electrons I'm looking at. So here's my inner electrons. Here's my electron of interest. Okay, so I'd calculate Z star is Z minus S. Here we have 11 electrons, or well, it is 11 electrons, but so Z is 11 for sodium, minus 2, 4, 10, so 1. Here aluminum, again, we're looking at the same one. Now, so I've still got 10 electrons between me and the nucleus, but now there's 13 protons. So I see an effective nuclear charge of 3. Chlorine, again, same number of electrons between me and the nucleus, but now there's 17 protons. So 17 minus 10 is 7. So as we go across the row, the same electrons feel a stronger and stronger pull from the nucleus. And when we look at the periodicity of the periodic table, like the trends, you'll see that this trend shows up in like the size of the atoms and how greedy different elements are for electrons. So let's do some practice. So what is the SPDF notation for gallium? All right, well, we look up gallium and we say, okay, gallium is gallium's in row 4, and it's the first one in the P block. So remember, it's going to have everything that comes before it. So we'll start with the first row, and you get 1s2, and then next is 2s2, and the next is 2p6, 3s2, 3p6, 4s2, 3d10, 4p1. And so the easiest way to do it is just look and say gallium. Okay, gallium's in row 4. It's in the P block, and it's the first one in the P block. So we know it's 4p1, and then it's just everything that comes before that. Every single electron that comes before that. Okay. What's the effective nuclear charge of a 2s electron in sulfur? Okay. Well, we got to look up sulfur on the periodic table. And we find that sulfur is 16. Okay? So sulfur Z is 16. And then we look at a 2s electron, and what's in front of it is the 1s2. So there's 2 electrons in front of it. So 16 minus 2, and you get 14.